So today I'm going to be talking about terahertz spectroscopy and how we can apply this to environmental problems. And really what I'm going to try to do is just give an overview of the technique and the type of information that we can get out of it. And I'm trying really hard to keep it at a level that everyone can take something away from this. But really, the thing I want to say up front is that, like Jenny mentioned, my research is really highly disciplinary. And so we have this tool, this terahertz spectroscopy tool, that we have in our lab, and it can be applied to many different areas. And we'll see this in the talk. And what I just want to kind of keep in everyone's mind is that everything we do starts from just a creative imagination. So we have no... In terms of the materials, there's nothing that says we're limited to only environmental problems or only drugs or only material science problems. We have this tool and we can apply it in any way that we want. So if anyone has any ideas and wants to talk about it, I am always more than willing to talk and find some new applications for kind of the science that we do. And with that, we can kind of jump right in. And first, the thing that is one of the most critical things to kind of keep in mind for what I'm doing and for what I'm going to present is that atoms and molecules are always moving, whether it's in a gas or a solid or a liquid, even in a solid where we kind of don't normally think about atoms moving, they are. Now, those motions are not necessarily in a solid, are not necessarily diffusive, so the atoms or molecules may not be flowing, but they oscillate around some minimum, like a pendulum. So this is an example that's kind of shown here, this animation, where two molecules are moving with respect to one another, and they just oscillate back and forth. Those motions, these what are called vibrational motions, are directly related to many material many physical phenomena. And one kind of real common one that everyone has observed is how things change size and shape upon heating and cooling. So we think of water as a common example. Water actually expands when you cool it, but that's weird. Most things, when you cool them, they shrink, like steel. And that thermal expansion and contraction that happens with temperature cycling is due to the atoms in that material moving. And when it's warm, they move a little bit more typically. And when they move a little bit more, that leads to the material expanding. And when it's cold, they move a little bit less, and that leads to material contracting. This has many obvious kind of applications. And one that I just stole off Wikipedia here is buckling in these steel train lines. So the railroad tracks over time, they expand, contract, and they bend and buckle, and that happens. What I just kind of have thrown up here is one way you can kind of visualize this motion. This comes from X-ray diffraction, so we can actually look at the structure of a molecule. And instead of the kind of common picture of atoms where we have them as spherical balls, in this picture, we have these elliptical type shapes, and that represents kind of that spherical atomic ball, that sphere moving. And so at low temperatures, at 90 Kelvin, so very cold liquid nitrogen, you see that particularly this one group, which is actually called the trifluoromethyl group, it rotates, and there's three atoms, and they kind of spin like a top. And so that's why you see that these ellipsoids kind of spread out around that rotation. As we heat it up, though, that rotation occurs with a larger amplitude. And so there's more motion, and so those ellipsoids get bigger. And so that's really what's happening at the atomic level when we heat and cool something. So you get more larger amplitude oscillations, which basically large amplitude oscillations lead to the molecules expanding a little bit. They're expanding their distance. If you understand the fundamental atomic level phenomenon, so what's happening, how much are the atoms intermolecular distances changing as a function of temperature, you can start to predict things like how much expansion there'll be or how much contraction there'll be as a function of temperature. If you start to know those things and know those parameters, then you can start designing solutions to avoid the railroad buckling. And so this is one thing that everyone has probably seen on roads and bridges. What they'll have are these anti-buckling devices. So it literally allows for some expansion or contraction without the road kind of buckling. So the way that my research kind of is designed to flow is we start from very fundamental. We want to know what the interactions are and how that leads to the types of dynamics and how these things kind of all play together. And then we build off that. So we go from understanding very fundamental atomic phenomena to leading into explaining bulk phenomena, and then finally to going to the solution phase. So the solution phase as in finding solutions to some problem. And this is what I mean, that we're not limited by the type of material. We can find out this information for a pharmaceutical molecule. We can find it out for plastics. We can find it out for semiconductors. So I kind of joke that we'll stick anything in the beam. You know, we'll throw anything in our laser beam and we'll try to understand what's happening. And then just once you know the fundamental forces, all you need to know is what problem you need to kind of figure out, and then figure out how those two kind of are interlinked. And that's the theme of everything that I'm going to kind of present today. So what tools are we using? What are the techniques? So in the lab, in my lab here, we have some laser beams, and we do what's called vibrational spectroscopy, particularly at terahertz frequencies. So it's far infrared. And we have a few different lasers in our lab, a few different experimental setups. One is a custom one where we can kind of build an experiment to have any sort of utility that we need. And that's one aspect of our research, is actually building new instruments, building new sensors, building new devices. And then we also have some commercial spectrometers where it's just, we literally throw anything in the beam and we can get data in seconds. So we have kind of a really nice toolkit. And for anyone, I find when I'm telling this now to incoming graduate students, I show them this, they don't laugh at this anymore. So I feel like I'm getting old, but you know, we're using laser beams, Dr. Evil. And then what we also do, which makes us a little bit unique, is that we don't only do experiments, we also do simulations. And we use what's called density functional theory for the most part, which are quantum mechanical simulations. We have our own kind of small computer cluster on campus in our lab, but we also use the VACC, which is the supercomputer, campus-wide supercomputer. And then on occasion, we'll use national supercomputing resources. So these are kind of the tools that we have. And when we bring those two things together, I'll kind of explain more how we do that in a couple of slides. But first, I just want to kind of orient everyone to where the terahertz region is in the electromagnetic spectrum. So for anyone who doesn't know this, light is a wave, and it has a wavelength, and the wavelength of light dictates basically what color of light you have. And so what most humans are used to thinking about is visible light, which kind of occurs in this kind of small window over here on the frequency spectrum or the wavelength spectrum. At higher frequencies and smaller wavelengths, you have higher energy radiation, gamma rays, X-rays, UV rays. And then going to lower frequencies from what we're used to visible, we go into the infrared, and then the terahertz, and then microwave and radio waves. And this is going to longer wavelengths. So the terahertz region falls kind of in between this higher energy light, infrared and visible light, and the lower energy light, radios and microwaves. And that leads to quite a few interesting things. The first is that for the longest time, until maybe the mid 1990s, this region was known as the terahertz gap, because there was no good way, there was no really general ways of actually making this type of light and detecting this type of light. Humans are very good at making radio waves and microwaves, and for that we typically use electronics. So you have some electronic circuit and you have some antenna, and that generates radio waves and microwaves. But going beyond the microwave region, it's too much energy to produce on an electronic circuit board, and so that's why the gap kind of ended at the microwave region. On the higher energy side, we typically use semiconductors to generate visible light. For example, LEDs, light emitting diodes, are a semiconductor. We have lots and lots of experience, again, as a human race at making these semiconductors. The problem is that when we try to make a semiconductor that operates, or an LED that operates at terahertz frequencies, it's too low in energy, and so it doesn't work. And so that's why there was a gap kind of on both sides. Over the course of the 90s and the 2000s, people have figured out some tricks for how we can make these, and now it's actually come to the point where terahertz is actually a commercially viable thing now. So in the early 2000s, even the early 2010s, if you want to do terahertz spectroscopy or do any type of terahertz research, you had to be really good at optics. You had to build a custom instrument. It would cost you at least $400,000, $500,000. You would need a big space to build this complex setup. Now it's come down, the technology has advanced, laser technology has advanced to us being able to buy a commercial instrument for $50,000, $60,000. So much cheaper than 400. Still expensive, but it now is in kind of the range of analytical instruments, what they cost. So it's really booming in popularity, and there's so much you can do, and I'll talk about that on the next slide, because of the properties of this type of light. One thing that's actually really interesting is where it falls, it actually borrows properties from the radio wave and microwave region, and it borrows properties from the higher frequency region, the infrared and visible regions. What it borrows from the radio and the microwave regions is that most materials are actually transparent to terahertz. So you can do terahertz spectroscopy, you can do measurements through walls, or you can do them through packaging. There's lots of security applications. Putting terahertz scanners in airports is one area of research. On the other side, you can do what's called spectroscopy, and that's what I'm going to talk a lot about. So I'll kind of hold off for a second there. But because it's a relatively new technique and we're really only scratching the surface, there is so much we can do with this type of radiation. Not only spectroscopy, which what I'm going to talk about, but tons of other things. So I kind of mentioned briefly, a lot of things are transparent. So imaging is one application of terahertz. And so you might not be able to see it very, very well, but this is an image of a visible light image of a man. And this is a terahertz image on the right of the same man, and hidden inside of the newspaper is a knife that you can detect with terahertz. One other cool thing that I like to mention that's really interesting with terahertz, we're all hearing now about 5G. T-Mobile, AT&T is talking about 5G and rolling out 5G. Going beyond 5G actually goes into the terahertz region of the spectrum. So there is lots and lots of work regarding terahertz communications, designing antennas and receivers, and figuring out what happens when you have a terahertz receiver and it's snowing. That sounds kind of funny, but this is how new the field is, that people don't really know, what happens to the signal when it's snowing or when it's raining or when it's humid. So there's lots of cool things being done with terahertz in that regard. So again, I said in the beginning, and this is a place I'll say it again, lots of room for creative thought and imagination in the terahertz sciences. To kind of show you, terahertz radiation actually passes through a lot of materials. So this is it passing through cardboard, fabric, and drywall. And I just went into the lab and put these in front of the beam, and we get signal through all of these. And I won't bore you with what the signal means, but we get signal through. That's kind of all you need to know. One cool thing with Terahertz, because it's transparent, is when I was a postdoc, we set up an experiment where we actually watch water go into a tablet, into a drug tablet, to try to understand what happens to that tablet as it's dissolving. And so what we basically do is we shine the terahertz light on, we detect it, and we can actually watch what this kind of signal here that's moving up in time is actually the water progressing into the tablet. So we can get understanding about how complex processes occur. All of that has nothing really to do with what I'm going to talk about. But what I'm going to talk about is terahertz spectroscopy. And what that is looking at these motions of molecules, and specifically the motions of molecules at terahertz frequencies. And this is just another example of a terahertz motion, where the thing I want to point out is that there's lots of things moving. There's entire side chains moving, and the entire molecule is kind of bending and moving. So that's actually really unique. And I'll come back to that as we get into the details a bit more. But one kind of thing that an early application of terahertz that stands out is these motions depend on, at the simplest case, two molecules moving with respect to each other. And so what that means is that if you have two different molecular structures, even it's the same molecule, but they're just packed in three-dimensional space differently, that leads to different types of motions, and those motions happen at different frequencies or different energies. And so what I'm kind of showing you here is it's actually glutamic acid. It's the basis for MSG. It's a amino acid. And I can go into the lab and I can go to the chemical supplier and I can buy glutamic acid. And that's what I get. I get a bottle of glutamic acid and it's a solid. But glutamic acid can actually form two different 3D structures, the same molecule, but it can pack differently. And that's what's kind of shown here. There's an alpha form and a beta form. And you could see that this is what's called a unit cell. It comes from a crystal. So this is actually a crystal that is infinite in 3 dimensions, but this is the two building blocks. These unit cells are different. And so that leads to different motions, which leads to different terahertz data. And that's what's shown on the left here. And you can kind of see, even someone who's not trained can see that they're different. And so if you were trying to identify, maybe this happens in the pharmaceutical industry where different packing leads to different solubilities. So they want to know what form they're making in their drugs so that when you go to take it, it's dissolving the way they designed it to dissolve instead of something different. And so one application is just throwing a terahertz spectrometer on a factory line. And if you wanted, for example, the beta form, you would just look for the presence of this peak that doesn't exist in the alpha form. This is, in a way, a complement to X-ray diffraction for people who know that, in that we're not actually probing the structures, we're actually probing the motions, but because different structures have different motions, we're indirectly probing structure with terahertz. So one thing that's relevant to some people here maybe is minerals. So mineral space, there are lots and lots of different minerals. Oftentimes you have different minerals that only differ by maybe the concentration of relative concentration of two ions, or the amount of water that's crystallized in it. And so, for example, one thing that we've done is we looked at iron sulfate. And we didn't do this for soil chemistry. We did it actually because iron sulfate's found in ink, and it actually over time degrades and ruins like parchment. So we were doing this from an art preservation standpoint. And now the thing about this is these two forms that I'm giving you as an example, there's a tetrahydrate with 4 water molecules per iron sulfate, and there's a heptahydrate with 7 water molecules per iron sulfate. Both of these have iron sulfate. Both of these have water molecules. So if you were doing some type of elemental analysis, you would find iron and sulfur and water in both of these. But they're different. They're different minerals. They have different properties. They have different structures, as you can see. And so one thing that again, just like I showed with glutamic acid, the two different structures have completely different terahertz spectra. And so in real life applications, you get a mix in a real world sample. You get some heptahydrate, some tetrahydrate, you might get some anhydrous with no waters. And what we can do is, by knowing what the individual spectra look like, we can understand complex mixtures. So this spectra in the middle actually has a mixture of both forms. So we can actually understand and quantitatively extract out concentrations. We also do simulations, and I won't spend too much time on this, but we do lots of simulations to understand the terahertz spectra, to predict the properties of materials. And we use the experimental terahertz data to validate the theory. And we also use the theory to validate the experiments. We kind of go back and forth. But when we do that, we get a really powerful data set, because if we use the experiment to validate the theory, that means that lots of things that the theory calculates that we can't measure experimentally, we can trust. And we can trust it with a high degree of accuracy, because it's really, really challenging to predict terahertz spectra. You have to have a very, very good simulation. And so if we do that successfully, we can actually trust the data that we've simulated and go the next step and start extracting more complicated information out. So we can actually use this as a kind of powerful tool set combined. So the first kind of thing that I was talking about are these things called porous materials. Basically what you do is you take a metal ion, you take some organic molecule, you mix them together, and they form these frameworks. And you can vary the size and shape of these frameworks and the properties of these frameworks just by varying what metal you use and what organic molecule you use. And so you can generate all sorts of different shapes and sizes and topologies just by changing the chemistry a little bit. And so this is just one example. Here's another example. It's a really bad joke, but I call it a holy MOF. Bad joke, but this was a metal organic framework, a MOF that's used for catalysis. And now these metal organic frameworks are really promising, because they introduce these porous void spaces, which is shown here in this kind of teal color. So that's just an empty space that's formed by this framework. So one really, really popular application is gas storage, and particularly sequestering CO2 is the goal, right? Pulling CO2 out of the air, carbon dioxide. You could also use it to purify dirty solutions. So there's applications where people have used MOFs to extract toxic chemicals out of runoff, industrial runoff. People have used these as drug delivery vehicles. And their utility comes from the fact that you can tune the property by changing the metal cation, the organic molecule, which changes the size and shape of the pore. So you have lots of degrees of customization. One really cool application is actually passive water harvesting. So there are a series of MOFs that have been discovered, and more are coming out every day, that operate, they absorb water based on the relative humidity of the air, based on the percentage of the humidity of the air. And so they tend to operate over a really narrow frequency range. So this is relative humidity and water uptake. And you see this one right around 20%. If the humidity is above 20%, it uptakes 400 grams of water per kilogram of material. If the relative humidity drops below 20%, though, it absorbs zero, basically, water. So it actually releases the water. And so there's actually a pretty cool group out there that did some work where they actually went into the Arizona desert. They designed a MOF that works at the relative humidity range of the Arizona desert during the day and night. And it absorbs water at night when the humidity goes up, and it passively releases water during the day when the humidity drops. And the only reason why you see a solar cell here is there's a fan to help increase the airflow over the material. So literally produces clean water magically out of thin air. One thing that we're doing in my lab is trying to understand where the waters actually go, the atomic positions of the waters inside these materials. And it turns out that for one of these materials, there's a bit of ambiguity in where the water's going. You really can't see it in this diagram, I know, but there's very subtle differences in where the water molecules go. And that is important to know if you want to start figuring out, okay, how can I improve the performance? I need to know where the water molecules are going, what they're being attracted to, what the forces are in between the water and the framework. So why does it happen? And then how can you improve it? These two structures that are they're potentially right, using common techniques such as X-ray diffraction doesn't really give you any information. They give you exactly the same structure because the difference is so subtle. It's such a subtle difference between these two potential targets. But that very subtle difference is reflected in the terahertz data because it leads to different motions depending on where the water molecules are. And so this is the experimental spectrum. These are two simulated ones. We have experiments now, but you see that, again, you don't have to be an expert to see that the blue curve on the right here doesn't predict any peaks down in this region where we see them experimentally, but the black curve does. And so we can now start to use this to understand structures. Another application is pulling CO2 out of the air. This is kind of the big one, sequestering CO2. And so for this is actually a material that we're looking into called collaborators. And I actually found out 2 days ago that we just got a $700,000 NSF grant to look at these. So we're going to be doing this for the next kind of 3 years. But again, these things form porous voids in the crystal, and those porous voids can trap gas molecules. What we found is that those porous voids, when they absorb CO2, again, just like the previous example, it completely changes the terahertz spectra. So on the top here is the spectrum for a empty framework, and the bottom here is the terahertz spectrum for a loaded framework where the CO2 is in it, where the top one has no CO2. The voids are empty. And again, it's a drastic difference between the two. So we can very clearly tell when we have one or the other. But even more interestingly is that there is a terahertz mode where the gas molecule, with CO2 here, you see it moving, it kind of rattles around in that void. And this is just one motion. There's actually a few different ones where it rattles around in different directions. And that corresponds to a vibration that occurs at terahertz frequencies. So exactly what we're kind of probing. There's a lot of information on this, and it may be over some people's heads, but basically what we found is that gas rattling is directly related to the absorption of more gas molecules into the solid. So one of the things we want to look at is, instead of using heat or temperature to trap or absorb gas molecules, can we put this sample inside this low frequency laser beam that's not heating the sample at all, but it's exciting these motions to kick off or kick out molecules or pull them into the framework. Kind of the last thing that I'll go into really briefly, if I'm, yeah, I got 3 minutes. Okay, perfect. Is what we're kind of going into with looking at microplastics. So we're interested in trying to understand these microplastics because they're a huge, huge, huge environmental threat. They are arguably one of the biggest environmental threats, because what it is, it's plastic particles that don't degrade. They don't break down chemically. They just get smaller and smaller, kind of like through friction forces. They grind down, erosion, just like rocks and minerals. And they stick around for hundreds of thousands of years in theory, because of how stable the polymers are. They are found everywhere. And this is just one map, and you can go on Google and find tons of maps from everything. This is a world map, but I've seen papers where they've looked at one river in Germany and have found microplastics everywhere, inside of fish, even inside of some humans. They found microplastic particles. So it's a huge problem. And one of the things that we're trying to do is to use the terahertz motions to understand why they're so stable. Why are these polymers so stable? What makes them stable? And then how can we go from understanding what makes them stable to then designing solutions and catalysts to break them down, to get rid of them once and for all, for good. And so for this, I'll go kind of quick. What we're trying to look at is elasticity. And so if you think about measuring elasticity on a bulk scale for like a block of steel, what you would do on it is you would push on it and see how much force you needed to apply to get it to deform. And that's great, and it works great on the bulk scale. But to do that at the atomic scale is very difficult. It's difficult to push and pull on a single molecule. You can do it, but it's really, really challenging. But what elasticity really is, again, at the atomic level, it's how much resistance there is for two molecules to push towards each other. If it's easy for two molecules to get closer, then it's easy to push the bulk together, because then every molecule will just get a little closer to its neighbor. If there's a big repulsive force between two molecules, like in steel, it's hard to push it because the molecules don't want to get close together. They want to stay where they are. So elasticity gives you information about bond strengths. So we looked at two polymers. What we found is that at terahertz frequencies, there's a vibration like a spring of the entire polymer. So what we realize is we can use this vibration to actually predict the elasticity and actually determine, not even predict, directly determine the elasticity, because it's just like a spring. And if you have the equations that you know how to get the elasticity of a spring, you have the equations to get the elasticity of this polymer. It's exactly the same thing. It turns out that we got values for the Young's modulus, how stiff it is, of 5 and 10 for these two polymers we looked at, which agrees perfectly with a real elastic measurement. Now, the thing that we didn't push or pull on single molecules. I didn't touch the sample. We really just flicked on the laser, shined some light on the material, figured out what energy that vibration happens at, and then just did some algebra to back out elasticity. So it's a pretty cool technique. We can then understand why it happens. It comes down to chemistry, what's going on with this bond, and this is kind of the last thing I'll say. But if you just look at this intuitively, think about these polymers as a rubber band, right? And on the polymer on the bottom is a rubber band that's already stretched out. So if you want to pull a rubber band that's already stretched out further, it's harder than a rubber band that's just kind of at rest and kind of flopping around. You can push and pull on that floppy rubber band a lot easier. So that's really the difference. So the difference comes down to the chemistry at its core, and that propagates through all the way up through macro like scale events. Finally, just kind of the conclusions. I'll just say that terahertz, I hope, it's really fun and exciting and interesting. There's lots of different aspects to terahertz, things you can do. There's lots of different possibilities. And what's important to this community is that it's not really been commonly applied to the environmental sciences, and there's no reason why, other than no one's done it. So let's change it. And I'm very enthusiastic about finding collaborators to do some cool things with some positive impacts. With that, I'll thank my group and the people who paid for it, and I'm happy to answer any questions.
Wow, thank you so much, Michael, for such a stimulating talk. Definitely a lot sparked from that. So since other people can't clap, I'm just gonna offer their applause from my end. So thank you for that, and thank you everyone for joining. Please go ahead and pop a question in the chat. I did want to kick off with one of my own, which is just, I can already see how there's relevance with soils, which I study, and particularly clay minerals, which are really hard to study in heterogeneous mixtures on using powder XRD, for example. But I'm wondering about, I have these amorphous iron and organic matter compounds in the soils that I think might be really good at capturing phosphorus. What about poorly crystalline materials?
That is a fantastic question. So the difference between crystalline and amorphous materials is that when you have a crystal, each unit cell is doing the same thing, right? So each unit cell has each unit cell has the same type of motions, and it happens in every unit cell. And so that's how we get those nice big peaks, because that's always happening. With amorphous materials, every molecule is in its own environment. And so every molecule is doing its own type of motion. And what that leads to is basically kind of a broad absorption feature. Now, again, the field is so new that 6 years ago, I would have said amorphous materials, we can't get any useful information out. But that's changed over the last maybe 3 or 4 years. So now we can actually have developed some new techniques, both in my lab and the field in general, for understanding what's happening with amorphous material. And for that, typically we'll do like variable temperature stuff and see how that featureless peak changes as a function of temperature, which gives us information about kind of how bond strengths are changing and things like that. So we can definitely get useful information out of amorphous materials. It's just not as clean and pretty, I would say.
Very cool. Thank you for that answer. And we have 2 additional questions in the Q&A box. Continue to throw those in. I'll just go in order. Jeremy asked, what exactly, going back to that slide, the man holding the knife, what made the newspaper transparent to terahertz imaging, but not the human? I think because they're both carbon-based. Is it water content or related to density?
Yeah, it's again a great question. So, there's a couple of things here. So there are some materials that are completely transparent to terahertz. For example, like quartz, crystalline quartz is completely transparent to terahertz. We actually use it as windows on our spectrometer. Other things like paper, which is made of cellulose, which is typically amorphous, maybe it absorbs at a very, one peak, one narrow frequency range it absorbs, but other frequencies will get through. So if you're using a broadband source, you might lose a little bit at one frequency, but you get some back at a different frequency. Water, atmospheric water, actually absorbs terahertz very, very strongly. And that's one kind of problem with it, is that it's actually rotational transitions in water, atmospheric water, that are excited at terahertz frequencies. So that's one actually kind of problem big for the terahertz communications people, because they have to find the frequency ranges that water doesn't absorb terahertz, because that's where they want to operate in. In terms of the imaging, what you're doing, some things might have a little bit of absorption, but what you actually do with the imaging is you're looking at we use pulsed radiation. So we send out pulses and we wait for them to come back. So it's kind of like sonar or radar. And so based on how long it takes to go and come back, that tells us how much it traveled. And so if there is something that absorbs a little bit, that's not such a big deal, because as long as we get the signal to come back, we can get the imaging information. If that answers the question. Thank you.
Awesome, thank you. And then we have some questions from Taylor. By the way, the question you just answered was from Jeremy, and he also said, thank you for a great talk. Taylor asks, says that carbon capture is definitely exciting. And what does that material look like, including the MOS that can absorb CO2? Can it be stored efficiently over longer terms, or transformed into other forms of carbon?
That's a great question too. So with these MOFs, what makes them kind of really neat is that, from this kind of picture, and it's literally, I'm a really bad kind of real chemist. Like, you won't typically see me with a beaker making things, but I can even make some of these MOFs, because what you do is you take some powdered metal, you take some powdered organic molecule, you mix them together in solution, and they dissolve, and then out comes this MOF framework crystals. They just often precipitate right out. So it's super easy. What the material looks like that absorb CO2, there are so many different ones that absorb CO2, just varying in their efficiency, how much they can absorb, what pressures they operate at, what temperatures they operate at. And again, that's where kind of the ability to tune the structure super easily is so powerful, because if you have, for example, it may be tough to see in this MOF, but the organic linker at the end of this molecule, there's this what's called a methyl group, a CH3. It's really easy to change that functional group to make it a OH, to make it to take it off, to put something else there. So when you do that, you really don't change the whole topology so dramatically. But what you're doing is the CO2 is going to come in and it kind of gets attracted to these molecules. And so if you know where the CO2 is going, then you can maybe change that functional group to something to make that attraction stronger, and then it will stick harder, or make it weaker if you don't want it to stick harder. And so there's so much functionality with these, and that's where the utility really is, where you can, one, what we're trying to do is do it from, let's understand what forces are dominating this, and then rationally design the MOFs. Other people in the field, because I am by far not even close to the only one doing this, are just making tons of different ones and screening for what works best. And so there are some companies now that are forming, and CO2 is the dream, right? But there are some companies that are forming that are using this property to actually generate very, very pure gases for like synthesis in semiconductor industry. So they really need very, very 100% purity, basically, gas. And if they design a MOF that selectively binds one gas molecule versus a different type of gas molecule, you can purify things that way. So if you want to store it long-term, the answer is it could be designed that way. And it might be that, just like the water absorbing MOF, which I have here, you have it so that it absorbs at a relative humidity of 40%, or you could think about a relative concentration of CO2. And then you just keep them off in that environment with a relative concentration. So you store as much CO2 as you can, you load it, and then you keep a container a little bit overly pressurized. So it keeps all the CO2 kind of trapped in the container or in the material. That's just one example, but you can vary it pretty easily.
Fantastic. Taylor had another question, which I believe was related to mine, just seeing biogeochemists loving this potential, maybe even to measure different nitrogen forms in water or soils and trace their transformations through the nitrogen cycle. Is that possible? Quantifying the amounts of ammonium versus nitrates versus nitrites, et cetera.
Yeah, so I think that this is where actually it is super powerful, because the high level, or the whatever it is, high level or low level idea is there is some nitrate or ammonium or phosphorus in the soil, and that's what gets in a report or in a fertilizer, right? It tells you what's in it, but it doesn't tell you what form it's in, right? So it doesn't tell you if it's a crystal. It doesn't tell you if it's ammonium nitrate or ammonium, some other counter ion. It could be a mineral with nitrogen in it. So where Terahertz comes in is I can actually tell you exactly what the bulk structure is, exactly what form it's in. And so, it might be that some ammonium gets trapped in a crystal and it won't ever leach because it's in some mineral that doesn't dissolve and it gets trapped. Or it could be the other case where it will just instantly leach into water. And so in that case, just by saying, okay, you have 20% ammonium doesn't actually give you information about what the long-term effects are. It just says you have some ammonium here. But if you know exactly how that ammonium is structured at the atomic level, who knows what you can do, right? The possibility, it gives you so much more data to work with.
Awesome. That's great. Another question from Jeremy, who asks about potential health effects, and maybe he's thinking about, I thought this was rumored, because my impression is that non-ionizing radiation doesn't necessarily pose a health threat, but he does bring up electromagnetic radiation concerns, and the understanding that the higher the frequency, the higher the potential for cellular damage. Now, this would be actually a lower or a longer wave, correct?
Yeah, exactly. Lower frequency, longer wave. So this, we get into the terahertz field. Some people in terahertz field will get into some like Twitter wars with some people over this, that airport scanners are unzipping your DNA and messing with your cells. Let me put it to you a different way. So at room temperature, in the air right now around me is about a little under like 5 terahertz of energy equivalent. We operate from like 0.3 to 3 terahertz. So we're not doing anything that you're not getting already just by walking around on a warm day. You go, that's not even considering the sunlight. I'm just saying there is like an ambient energy from temperature in the air, and that is higher than the frequencies that we're using. So there is no real health concerns. There is no, look, you can people have shown, and theoretically mostly, that if you use ultra strong terahertz electric fields, like so big that they actually like can etch metal, that's a very different process than like the frequency of light is being absorbed and messing with your body. That's the electric field strength is actually like you have some basically like a magnet, a strong magnet that pulls particles away. We can't even come close to making electric fields that have that high of field strength. But on the terms of the actual frequency that like the photons of light have, your body doesn't even feel them. We've done measurements. So we've actually done some measurements, I didn't talk about them, where we've shown that we can actually excite those motions to do something. So like we've excited those motions to promote transitions between two structures. But what's happening is that we're exciting that motion of the molecules. It's not that we're raising the temperature of the sample. So it's a good question, and it's a marginal, I guess, concern, but we never operate with enough of an electric field strength to do any kind of damage. You could stick your hand in a terahertz beam, you would never feel anything. We've measured the temperature of our samples with a really high accuracy. They don't heat up, even if we keep them in the beam all day. So you get nothing. And it's the same thing with like the scanners in the airport. So the body scanners now, you have to go put your hands up over your head. Those are actually right on the edge of terahertz range. One time I was actually flying, and it kind of made me laugh because the person I found out on the plane was actually an MD, didn't want to go in the body scanner because they were afraid of the radiation from it. And I didn't have the heart to tell them that they get way more radiation from being on the plane than they do spending a second in the body scanner. So no, the answer is no, basically. There's no real health concerns.
That's also really good to know about it sounds like it's a very non-destructive approach.
Completely non-destructive, non-invasive. So like we have a project where we're looking at artwork and understanding artwork, and they love it because we're not using, the real method is X-ray, and that will destroy the artwork, and we don't have to. We can do it completely non-invasive, non-ionizing, nothing happens.
Awesome. We have another question, and I just want to open it up for one more beyond this one that I'm about to read, in case anyone has a question. But this comes from an anonymous attendee who says that ecologists use stable isotopes to trace where species come from, and they use radioactive isotopes to actively label individuals or seeds or whole grassland systems. And this person wonders, could you use this approach to label things and trace their movements, certified timber or fish, poached endangered species, and detect the label quickly with a simple laser exposure or something?
I think that actually The answer is yes, but I think that you don't actually even need radioisotopes. As long as you have just an isotope, it doesn't have to be radioactive, because actually the energy of the vibration or the frequency, or where that peak, we see that peak come in, depends actually on the mass of what's moving. So if, you know, for example, everything in nature is, we'll just assume it's perfect and it's like carbon 12. If you threw a carbon 13 on something you were interested in, that would actually result in the peak shifting a little bit compared to the carbon 12 peak. And so just by analyzing that peak shift, and we can actually figure out, you know, where things go.
Neat. One last question, and Robert says it's probably too early for application, but about that cool selective water absorber, which I really want to go find that article now. He says, I think you said that the night to day air temperature changes fully drive it. Is that right?
That is right. The only kind of power involved in that was just the fan. So the fan blows the air over the material. The intrinsic chemical properties of the material result in it absorbing water at a certain humidity, and at a lower humidity, it releases. And so it's just air, and it comes out. It's like RO water. It's perfectly pure. It's pure water.
Wow, excellent. All right. On behalf of the Gund Institute, I want to thank Michael and everyone who joined us online. We'll have the video and podcast of today's talk available next week. Please join us again next Friday for our next Gund Exchange with Macmillan scholar Carolyn Finney, whose talk, Being Black and Seeing Green, Risking to Gain and Playing the Long Game, will be on April 16th. So thanks again so much for an engaging talk, Michael, and hope to see you all at our next talk.
Thanks, Jenny. Thanks for being a great moderator.
Sure thing. Have a good weekend.
You too.